All right, hello everyone. Now that we know a little bit about linear regression, more so the basics, slope, y-intercept, and using that line of best fit, what we're going to talk about today are some details regarding linear regression. So this might seem obvious, but remember when we're talking about linear regression is just for lines. There are different types of regression for different shapes of graphs, but when we're doing linear regression, we want to make sure that we have a linear pattern within our scatter plot. A curved relationship may only be visible if you look at the residual plot. So for example, if we look at this bottom left scatter plot, it looks like it might be somewhat linear, but as we look at the right, which is the corresponding residual plot, we see that there's definitely a curved pattern here. So when it comes to determining do we have a linear pattern or do we not, it's great to look at our scatter plot, but the residual plot is going to tell us for sure whether we have a truly linear model or not. So when it comes to determining, do we have a linear pattern, does it make sense to find a linear regression line? The residuals are going to have the final say in this. So even if a plot looks linear, we want to check the residual plot when it's available to us. And while looking at the scatter plot to determine linearity is good, the residual plot gives the final say on whether or not a linear pattern is present and whether or not a linear model is appropriate. So within our residual plot, of course, it's very useful in determining, do we have a linear pattern? Do we not? Is it okay to find a line of best fit or is it not? We can also find groups within our residual plot. So if we were to not color code this residual plot, it would still look like random scatter, which is a good thing, leaning towards a linear pattern being appropriate. But residual plots are useful for finding subsets within our data. And this allows us to analyze groups separately instead of all together. So in this case, if we look at our blue points on the residual plot, that's where most of our data is, and we see that it follows a very linear pattern. But down below, we have a small subset of points that have a very low or negative residual, and on the high end, we have very high residuals. So instead of looking at our data set as a whole, we might want to break these up into subsets and study each individual group. So just as an example of this, in this figure, we have the calories and sugar for 3 different shelves of cereal at a supermarket. So if we look at the blue or line number 1, we see it's a relatively flat, not very high slope pattern, and same thing with the red on the second shelf. But if we look at the third shelf, so the third from the top, that's going to be our green one, and we see that has a much more significant rate of change. So if you think about how they market different cereals at a store, typically kids' cereals are going to be a little higher in sugar and calories for that matter, and that would make sense that as sugar increases, calories also increase. So if we're talking about where are children's cereals located on the different shelves, well, they're probably going to be lower towards the bottom so that kids can see them and hopefully take a box and stick it in mom and dad's cart. So again, this just shows that as a whole, yes, we have a nice linear pattern, but we're also able to break up into subsets to determine is there patterns within, in this case, different shelves of cereal. One really important topic when it comes to linear regression is the idea of extrapolation. And this is where we are reaching beyond the data that we have already recorded. So when it comes to a linear pattern, we can see that within the data we've collected, but we cannot assume that that's going to happen beyond the data we've collected. So the further away that our new x value is from the mean of our already collected x values, that means we're going to trust what's going to happen in the future a little bit less. So the further out we go, the less predictable or less reliable that prediction becomes. And once we venture into new X territory, this is called extrapolation. So for example, in my table here, I've collected data for 4 years, ages 0, 1, 2, and 3, and the corresponding weights of each of those ages. So if we were to put a scatter plot together, we would see a pretty linear pattern. But what we can't assume is if we found the line of best fit here, and for example, we plugged in 70 years old, that would probably not be a very reliable estimate because we know as you get older, you don't necessarily see the same gains from one year to the next in weight. Here's another example of where extrapolation might get us into a little bit of trouble. So throughout the cross-country season, typically we have about 10 races. This past season we had 8 races with state included. But in this table, what we have is the race number, so the first race of the season, second, third, and so on, and the corresponding 5K time for each of those races. Okay, so as we see, as time goes on, this particular runner is getting faster and faster. And if we were to plug these numbers into our L1 and L2, the corresponding predicting of race time equation, or the linear regression equation, it is predicted race time equals negative 1.031 times the race number plus 20.830. And if we were to calculate the R value or the correlation, we'd see it's a very strong linear pattern in the negative direction. Our R value is negative 0.993. So almost a perfectly straight negative line. Well, let's say that at the end of the season, that's going to be race number 12 for us. And we want to use this linear pattern to determine what our predicted race time is on that 12th and final meet of the season. Well, if we put that in, our race number is 12. We simplify that, we get a predicted 5K race time of 8.458 minutes. For those who might not be familiar, a 5K is just over 3 miles. So for someone to run that in 8.458 minutes, it is impossible, okay? So again, the further away our X values get from what we've already recorded, the less reliable that prediction is going to be. This might be a good model for races 1 through 4, maybe to race number 5, but if we get into the 10th, 11th, 12th races, it's not going to be a very good estimate for us. So here's a comic that I found. It says, "My hobby is extrapolating. Yesterday, she had 0 husbands. Today, she got married, so she has 1 husband. So using extrapolation," which isn't correct here, of course, but if she were to extrapolate, tomorrow she would have 2 husbands, the next day 3 husbands, and so on. So another example of where extrapolating is not a good idea. So the last topic we have to talk about are outliers, leverage, and influential points. So we're familiar with the term outliers. So in the case of scatter plots, outlying points can strongly influence a regression. Even a single point far from the body of our data can dominate the analysis. So if we look at this scatter plot, we have a very, very linear pattern in the blue, but because of that one X at the very top, that's going to throw off our whole line of best fit equation. And any point that stands away from the others can be called an outlier, and it deserves your attention. Something kind of goofy is going on there. So when it comes to describing a scatter plot, we talked about direction, unusual features, form, and strength. Outliers refers to the U, or unusual features. In this particular example, our blue line includes the line of best fit if we were to exclude that one unusual red point at the top. If we include that red point, then that is where we get our red line of best fit. So as you can see, our slope is significantly changed. That outlier has a significant impact on our overall line of best fit formula. So an outlier, again, that is any point that stands away from the bulk of our data. So outliers, that's a pretty inclusive term. Basically, if you see a point or a cluster of points that are far away from most of our data, you can consider those to be outliers. Now, when it comes to a point having what's called leverage, a data point can also be unusual if its X value is far away from the mean of our X values. So such points are said to have high leverage. So in our example here in this scatter plot, we see that most of our data values have an X coordinate right around 1. But if we look far to the right, obviously that's going to be an outlier, but we would say this point has high leverage because its x-coordinate is really, really far away from most of our other x-coordinates. So a point can be an outlier and have leverage at the same time. And in this case, yes, it would have both of those. Now, a point with high leverage, so the x value is really, really far to the right or really, really far to the left compared to most of the other points. A point with high leverage has the potential to change the regression line. So it turns out that if we have that point in line with the rest of our data, with a point of high leverage, it can actually strengthen our correlation. Whereas if we have it outside of the general pattern of our scatter plot, it would actually weaken our correlation. So we say that a point is influential if omitting it or taking it out of our scatter plot gives us a very different model, okay? So if by putting that point in versus taking that point out has an extreme impact on our line of best fit formula, we would say that it is influential and it has a major effect on our model overall. So to illustrate this, this is our final slide. Let's say we're talking about Bigfoot. Okay, obviously Bigfoot has very big feet. So on the bottom left scatter plot, we have where we're looking at Bigfoot and he has a very high IQ. Well, we can see that because we have a general cluster of points, but our Bigfoot point has high leverage, it is in the top right. This is going to pull our line of best fit in that direction. Whereas if we look to the right, our points are still kind of in the same place. Well, if Bigfoot doesn't have a very high IQ, then that point is going to pull our line of best fit in the downward direction. So not only is that red X in either of these cases considered an outlier, it has high leverage because its X values are very, very far to the right relative to our other X values. And it would also be an influential point because it is determining the direction of our line of best fit, or it has a significant impact on the direction of our line of best fit.